I'd like to welcome you to Reno, and I hope that you get to enjoy the city and what it has to offer. As an introduction to this program this evening, I would like to acknowledge a lot of the people that were involved in putting this meeting together. As I mentioned, the group that you're in, if you could please stand. First of all, some of the people that were involved are the people in the program committee. So if you were in the participated in the program committee, if you could please stand. Two people in particular that I want to recognize are Judith Ulrich and Warren Haggard, who actually did more than what you normally ask a volunteer to do. Also, this meeting would not be possible without the workshop chairs. So if you were a chair of a workshop, if you could please stand. Thank you. Also, this meeting wouldn't be possible without the symposia chairs and co-chairs, without the tutorial chairs, without the topic coordinators, and without the reviewers. If you were any of the people in any of those groups, please stand right now. Of course, the meeting wouldn't be possible without the workshop speakers, the tutorial speakers, the symposia lead speakers, as well as the oral presenters and the poster presenters. This year we have a couple new things on the horizon. Tonight we will have our reception in the area where the exhibitors are to give us an opportunity to interact with some of the exhibitors. We also have this year 2 poster sessions, and the poster sessions have been moved to the daytime. So there's a poster session at noon on Friday and another one on Saturday morning. There are SIG meetings on Thursday at lunch, and then there's an all-SIG meeting, a group SIG meeting, Thursday at 5:15, and SIG members as well as those who are interested in learning more about special interest groups are invited. Of course, our ever-exciting business meeting is being held on Friday at 11 o'clock, and we hope to see you there. So with that, I would like to welcome you to the meeting and to introduce you to Joachim Kohn, the chair of the International Liaison Committee.
Thank you very much. As chair of the International Liaison Committee, I am extending a cordial welcome to our international participants. As you know, science is one of the endeavors of humanity where we cross the borders of national interest and come together to find important breakthroughs that will make life better for all of us. In the field of biomaterials, we actually have an international organization, and I think the field of biomaterials is one of the few scientific fields that have a formal worldwide organizational structure. As you know, many countries have national societies for biomaterials. These national societies of biomaterials are then part of IUS-BSE, the International Union of Societies for Biomaterials Science and Engineering. The IUS-BSE, among other functions, is involved in the organization of the World Biomaterials Congresses, the next of which will take place in Sydney, Australia in 2004. In order to celebrate our international collaboration, I would like to welcome the members of the Australian Society for Biomaterials, the Chinese Committee for Biomaterials, the European Society for Biomaterials, and the Japanese Society for Biomaterials, and finally also the Korean Society for Biomaterials. It is actually customary for us to ask our international dignitaries and guests to stand up and please be recognized. So if you are a member of the Australian Society for Biomaterials, the Chinese Committee, the European Society, the Japanese Society, or the Korean Society, would you please be so kind to stand up so that we can recognize and welcome you to our meeting. I indeed did. My apologies to our friends, the Canadians. If this would be a political meeting, my career would have come to an abrupt end. So I also want to welcome our Canadian friends, and thank you all for joining us. With this, let me introduce to you Fred Schoen, the chairman of the Award Ceremonies and Nominations Committee. Fred.
Well, thank you, Joachim. I'm delighted to have the privilege of presenting the 2003 Society for Biomaterials Awards. Let me just start by mentioning that I'm very grateful to the awards, nominations, and ceremonies committee members that this year included Jean Jacob, Martine LaBerge, Lane Smith, and Nick Ziatz, and appreciate their efforts and their judgment throughout. May I ask the awardees to come up one by one as I'm describing their contributions, except for the Clemson awardees, who should just stand because their awards will be presented later in the meeting at the time of their presentations. The first award is the 2003 Founders Award, which is given for long-term landmark contributions to the field of biomaterials. And this year's winner is Professor Edward Merrill of MIT. Dr. Merrill was cited for 45 years of fundamental research and innovation and contributions to education and training in biomaterials. In particular, he pioneered polyethylene oxide as a biomaterial and developed hydrogels and heparinized polymers for non-thrombogenic applications. Professor Merrill? The next award is the 2003 C. William Hall Award for contributions to the Society and its objectives. This year's awardee is Professor J. Lawrence Katz of the University of Missouri at Kansas City. Professor Katz was cited for his teaching, research, and service in biomaterials over a long-term career. Before his move to Kansas City, you all know him as the founding chair of the Department of Biomedical Engineering at Rensselaer Polytechnic Institute, and later the Dean of Engineering at Case Western Reserve University. He's also been a pioneer and leader in research in the biomechanics and biomaterials applications applied to hard tissue. He's also a past president of the Society for Biomaterials. Larry? The next award is the Award for Technology, Innovation, and Development, which recognizes successful applications of research in a product or technology that benefits patients. This year's awardee is Dr. Robert Ward of the Polymer Technology Group. He was cited for his innovative applications of polymer technology to a variety of medical devices, particularly cardiovascular devices. Dr. Ward? Now I'd like to acknowledge the Clemson Award winners. Once again, these awards will actually be given at their presentations. I urge you to check your program for the time of actually all of the awardees' presentations, Clemson and the other, and they're in the written program book on pages 74 and 75 as a group. The first Clemson Award winner that I'd like to acknowledge is the Award for Basic Research, Professor Joachim Cohn of Rutgers University. Professor Cohn was cited for his development of new synthetic biomaterials for medical devices, implanted drug or gene delivery systems, and tissue regeneration scaffolds. In particular, he's got a series of seminal recent papers that relate to combinatorial approaches and computer modeling of cell-polymer interactions. Joachim, congratulations. Following award is the Clemson Award for Applied Research. This year's awardee is Takehisa Matsuda from the Kyushu University in Japan. Dr. Matsuda was cited for research, development, and characterization of unique polymeric systems, and in particular the entire spectrum of in vivo and in vitro characterization. Recently, his work has taken him into surface modification and tissue engineering, in particular the analysis of cell-substrate interactions. Congratulations. The third Clemson Award is for contributions to the literature, and this year's winner is Professor Stephen Cook from Tulane University. Professor Cook was cited for his long-term outstanding productivity in orthopedic research and his more than 200 journal publications, one-third of which are actually in the leading journals of biomaterials and orthopedics, such as the Journal of Biomedical Materials Research and the Journal of Bone and Joint Surgery. Congratulations, Steve. I'd like to now continue with the Young Investigator Award that was awarded to Masayuki Yamoto from the Tokyo Women's Medical University in Japan. Incidentally, this award and the student awards that we'll be announcing were manuscript awards, and they were judged as a competition among manuscripts. And now the student awardees. The first is at the PhD level, and we actually had, we were unable to select among the three, actually there were more than three, but we could not select among the three top choices, so we're actually making 3 awards this year. The first is Rebecca Ann Caldwell from Clemson University. Second PhD student award is Ulrika Kluwer from the University of Connecticut Health Center. And the third PhD award will be given to Sharon Sagnella from Case Western Reserve.
This concludes this evening's portion of the award ceremony.
I'm Nicholas Pepas from the University of Texas at Austin. I'm the incoming president of the Society for Biomaterials, and it is my distinct pleasure to introduce to you today this year's winner of the Founders Award of the Society for Biomaterials, Edward Merrill. Professor Merrill is a native of Massachusetts. He was born in the area of New Bedford, Massachusetts. He attended Latin High School in Boston, and he got an AB, Bachelor's of Arts, from Harvard in classics and chemistry. In his senior year, one day he made a small mistake. By serendipity, he opened the door of the wrong classroom, and he entered a room where a professor, certain Professor McAdams from MIT, was giving a lecture on industrial technology. He was fascinated by the field, and he decided to join MIT as a graduate student in chemical engineering. He graduated from MIT with a PhD in 1947, went to W.R. Grace from 1947 to 50, and since 1950 he has been professor of chemical engineering at MIT. Merrill has been a giant in the field of bioengineering. He started working in bioengineering around 1958, mostly working with the Boston hospitals. His first excursion into bioengineering was in the area of blood rheology, but around 1965 he entered the field of artificial kidneys, and in the process he started studying membranes, biomembranes, and the first biomaterials for that particular application. Later, and especially with the explosion of funding in NIH, he turned his attentions towards hydrogels for biomedical applications. And he was the originator of the work on polyvinyl alcohol, the work on heparinized hydrogels, until his laboratory started producing the covalent heparinized PVA and other materials. There was only one technique available, and that was by Langergen and Ericsson. And that technique was, of course, an ionic technique that was not really very successful. He worked on PVP and so on. And it was in the 70s that, as a pioneer in the field, he recognized the importance of polyethylene oxide. And in a seminal paper, a classic paper in the field that he co-authored with Ed Saltzman of Harvard, he proposed that PEO is an excellent biomaterial, and the rest is history, as they say. That was a paper in the Transactions of SIO. He has received numerous awards. Our society has recognized him with the 1991 Clemson Award. The American Institute of Chemical Engineers has given him the Alpha Chi Sigma Award in 1984, the Bioengineering Award in 1998, and the 2001 award as a founder of the field of chemical engineering. It is therefore with great pleasure that I introduce to you today. I congratulate Professor Merrill, but for this particular occasion, I have asked three of my colleagues, Professor Alan Hoffman, past president of the Society for Biomaterials, and the first PhD student of Ed Merrill 46 years ago, and Mike Sefton, another one of his former PhD students, distinguished professor now at the University of Toronto. And I have also asked us to join on the podium Stu Cooper, who was an undergraduate student at MIT taking courses and being affected by Ed Merrill. These are the individuals representing a tremendous group of individuals that have been affected by Ed Merrill's educational contributions to the field and by his ability to be a great mentor. And at this point, I would like to ask Professor Alan Hoffman to come and address the audience and make a small presentation and a little surprise for Ed.
Thanks, Nick. It's a great pleasure to be here, and also it's a real privilege and honor for me to represent so many of Ed's students, past students, and their students, and their students' students, and it goes on and on. I've known Ed for 50 years, actually more than 50 years. We met in 1949 or 1950. Nick has only allowed me 1 or 2 minutes, so I have to go through a lot of history quickly. I simply want to say that he, first, for me, was a great teacher. And he taught me how to visualize molecules, which I think he's done for all of his students and all of us and our students, hopefully passed it on. This ability to see what a molecule looks like and think of what it's doing and how to make it do something you want it to do. And then I was a colleague of Ed's. I was on the faculty at the department. We shared an office together when he was a young assistant professor without tenure. I remember taking a lot of phone calls from a guy named Roe Wells over at BU talking about the rheology of blood, which is where Ed got into this field. And then he's just such a wonderful teacher, a wonderful mentor, and a great friend. And it gives me a great pleasure, Ed, to make this little surprise for you, which Nick has put together. If you'll come over here, I'll show it to you. Let me tell you what the surprise is before I unveil it. What it is a tree, an academic tree of Ed Merrill, starting with his teachers and going up through all of his students and their students and their students' students and so on. And this will be on display, so you'll have a chance to look at it up close. So it's not a surprise anymore. All right. And there it is. So let's thank Ed for all he's done.
Ed, this tree has been prepared by your students and the students of your students and contains 723 names of PhD students that have been affected by you. That list includes 57 children, 186 grandchildren, 354 great-grandchildren, and 126 great-great-grandchildren. It was designed by your great-granddaughter, Lisa Brannon Pepas. It includes 8 Clemson Awards recipients and 35 NSF Young Investigator Award recipients. It's our pleasure to present it to you.
Thank you so much.
And now we left a few minutes for your talk.
There we are. I'm delighted to be here, and I am enormously grateful to those who have organized this, and to my former students, and of course to the spark plug of this, Professor Nicholas Peppers. In the few minutes that I have to address you, I'm going to explain something out of Gilbert and Sullivan's Mikado, in which the Lord High Executioner, Coco, in his first song says, taken from a county jail by a set of curious chances, liberated then on bail, on my own recognizances. And so what I'm going to show you, or tell you about, is the bizarre set of chances whereby I went from an industrial engineer working on rubber cements and solutions to where I am today speaking about biomaterials. In this overall slide, which I'll cut into pieces as we go along, I start at the top with the Dewey and Almy W.R. Grace experience, in which I invented a viscometer for measuring the properties of their solutions and lattices made of rubber. And as you go down to the left-hand side of this, you will see that I wind up eventually working in antithrombogenic and non-thrombogenic materials for contact with blood. And on the right-hand side of this, you'll see that I wind up with ultra-high molecular weight polyethylene acetabular prostheses. And back in these days, this goes back to 1948, 49, 50, my employer, Dewey and Almy Chemical Company, which became W.R. Grace, helped me build a viscometer, which they call the Merrill viscometer. And there I am, at an earlier age, with more hair on my head, with the viscometer, which was a prototype. And it's a coaxial cylinder viscometer because we're dealing with solutions that are non-Newtonian. That is, it's like mayonnaise, yogurt, house paint. They have yield stresses in their shear thinning, so that therefore one has to measure viscosity as a function of the shear rate. And this evolved through the Brookfield Engineering Company in Stoughton to a prototype, which is called the Merrill Brookfield High Shear Viscometer. And in this slide that I show you, there's a sequence from the Merrill Brookfield viscometer to the GDM viscometer to blood rheology. And what happened was that when I went back from Dewey and Almy to MIT in 1950 to become an assistant professor, Dewey and Almy let me take the viscometer back with me, and I became involved in doing research at MIT on that. And one day, a Dr. Roe Wells of the Brigham Hospital called up my boss at Chem Engineering and asked if anyone knew anything about viscosity. And that brought me in contact with Roe Wells. And he had a problem of trying to measure the viscosity of human blood. And so we got into that, and between the Merrill Brookfield viscometer and the GDM viscometer, that's where Wells came in. Through the intervention of Draper, Charles Stark Draper, the head of the instrumentation lab at MIT, and the man for whom the Draper Prize, which Bob Langer just won, has been named, produced and gave to the chemical engineering department this marvelous viscometer for measuring the viscosity of blood at low shear rates. And there's Ed Gilliland, my boss, on the right. And here's yet another picture of Draper on the left and Gilliland on the right in that marvelous viscometer. Now, Roe Wells is doing a venopuncture on your humble servant. I'm having a blood sample taken. And that's one of countless that I was involved in back in those days. And our work on blood rheology, the viscosity of blood and how it's influenced and by what it's influenced, primarily fibrinogen and red cell content, led me, as Nick alluded to, into the artificial kidney and into the heart-lung machine, the membrane oxygenator. And as a consequence of that, back in the days when NIH funding was copious, I got a fairly large program going. But as you see, these little lines on the side indicate my interest in the problems of blood contact with foreign surfaces, which is inherent, of course, both in the artificial kidney and in the heart-lung machine, especially in both, for that matter. There's no way you can avoid it. So that led to the beginning of an investigation on what causes blood to clot in contact with surfaces. And that led me into an association with Dr. Edwin Salzman, who was, when I first met him, the associate director of the blood bank at the Massachusetts General Hospital, right across the river from MIT, as many of you know. And through Ed Salzman's help, I got samples of blood from patients normal and abnormal on which to carry out blood rheology studies. And as we got into this, Ed Salzman became my teacher on the principles of thrombosis. He wrote this famous text, Hemostasis and Thrombosis, with Tony Britton. And I started to realize that in looking at blood rheology, where I thought the principal components responsible for the viscous properties of blood were the red cell content and the fibrinogen plasma content. It turned out that, of course, in the real world, there are two elements involved of the formed elements, namely the white cells, which in disease states can become a major complication in the flow of blood, and platelets. And I hadn't realized how extremely important they are, so that in the ensuing years that we worked both on blood rheology and on trying to invent non-thrombogenic or antithrombogenic surfaces, I became increasingly aware of what turns platelets on. We became aware of the fact, for example, that if donors giving blood for analysis of platelet activity had by chance taken aspirin within a couple of days, it completely annulled the test because the platelets went to sleep. We lost a lot of time on that before that was proven. And over this period of time, there are a number of students, starting with Dick Buckles and then Ben Lips, who's now the Chief Executive Officer of Fresenius in artificial kidneys, my colleague Clark Colden, Gerson, Morgan, and Silliman, and you see around 1973 and 74, Nicholas Peppers and Michael Sefton. And the years 73 and 73 and 74 is particularly important because that's about the time that the Society for Biomaterials started to come into being. Now, it may be that's when Nick Peppers and Mike Sefton got out, and maybe they sent out the sparks that kind of helped set this off, but be that as it may, that's a fact. Some of these names are in capitals, and I'm just putting them in capitals to indicate those of my students who worked on biomaterials. This is not a complete list of all my students, but those who worked on biomaterials and who are also academics and professors, they are capitalized here. Of course, Clark Colden is my colleague at MIT. Mike Morgan is at University of Washington. And you know where Nick and mica. Now, in respect to the list of topics on which these students worked, most of them were designed for membranes, either with respect to dialysis in the kidney or passage of oxygen and carbon dioxide in the heart lung machine. But there was one side issue which I show here. By the way, starting up at the top, we start with rubber solutions and then go through the Merrill Brookfield, which we use to characterize Dewey and Almy's rubber solutions, and then we go down to the GDM viscometer. I might make the aside that the GDM viscometer was named for the inventors Gillinson, Dowalter, and Merrill. But other people have referred to it as the goddamn Merrill viscometer because of the fact that it was somewhat difficult to operate. It was fussy. In any case, using the GDM viscometer, we got involved in the study of hyaluronic acid and synovial fluid, both as synovial fluid as received from the joint. It's a lubricant in the knee, in the elbow, everywhere in the human body, and as purified substances. And we showed that the hyaluronic acid can be highly non-Newtonian. Its viscosity can be geothinning. We also showed, and this is the work of David Gibbs, that it can be highly viscoelastic. We had an oscillatory version of the GDM viscometer, and hyaluronic acid is a remarkable material. Now, since its purpose in the joint is to lubricate the cartilage and prevent cartilage from wearing on cartilage, that led us to think about when cartilage wears out, what can you do about it? And that's what carried Jim Bray and, far more importantly, Nick Pepys into working with polyvinyl alcohol hydrogels improved by, after irradiation and cross-linking, by crystallization. And Nick Pepys made some of these polyvinyl alcohol hydrogels as part of his doctoral thesis that were bulletproof almost. They were incredibly strong, and they were worked on significantly by others later on, including Nick. But to get back to our story, this is my first optometrist test. I bet no one can read this from any part of the room. So the title of it is Polyethylene Oxide as a Biomaterial. It came out in 1974. Nick referred to it already, and it was really the start of our great interest in polyethylene oxide as a biomaterial, and I culled out of the literature what I'd seen. And I'm not the first to have done this. I think Don Lyman was, and I think John Brash got into it before I did. All I did was to call public attention to it in this Transactions of the American Society for Artificial Internal Organs. And I have the pleasure of introducing you to polyethylene oxide. There it is in its extended form. Is it red? That doesn't show up well. We got CH2, CH2, oxygen, CH2, CH2, oxygen. The point of the thing is that it's a very symmetrical molecule. It crystallizes well. And also, go for it. Can someone forward this? Next slide, please. There we go. Got it. In its random coiling form, it's remarkably flexible. And it's a linear chain that has, as far as I know, the lowest characteristic ratio of about 4 of any known linear molecule. That is to say, it comes closest to the ideal chain that we know of. Whether this is relevant to its property as a biomaterial, I have yet to figure out, but it's a fact. And there I show it to you, beautifully coiled. Now, following this period, there are a number of students who worked on variations on a theme of polyethylene oxide with Virasada Costa, Najis Mahmood, Rick Bakela, Kathleen Dennison, Cynthia Sung, and Elliot Shakoff. And the Sung and Shakoff, I will talk about their work in a minute. Winding up more recently with Sue Sophia and Diana Rinsler-Yen on star molecules. But there's another thing about this slide. On the preceding slide, where I showed the pre-polyethylene oxide students, all of them were gentlemen. Not a one was a woman. Here we have 6 out of these 8 doctoral students as women and 2 men. Historically, for some reason, about 1974, there started to be a tremendous change at MIT and perhaps elsewhere in the world on the ratio of men to women in graduate school. And so I remark upon this because as I looked at the data, this is quite remarkable. It doesn't prove anything scientifically. I love them all, man and woman. But there is a picture, and you can obviously see me in the background, and next to me is Elliot Chaikoff, and in the your far right is Cynthia Sung. And Chaikoff and Sung worked on a form of polyethylene oxide, which was, the polyethylene oxide was the chain material in a two-component system where a silicone material was the covalent cross-linking material. So we have chains of PEO and junctions of silicone. The others here, you see 1, 2, 3 other women. They were all undergraduate students in our undergraduate research program, and they are irrelevant to this story, so I'll continue. But I can't continue without pointing out that on the far right you'll see a woman in a tall witch's hat. And here we have my students, Tim Donahue, Stephanie Sung, Cynthia Sung, who went on to NIH, and Deborah Savage. Why should I lug this on the stage? Because Deborah Savage is the only student, but a very good one, who was an undergraduate at Clemson. You perhaps heard of Clemson. Anyhow, that's why I bring it on, to make the connection that I have with Clemson. Now, going back to this material that we produce based on polyethylene oxide as the chain material and silicone as a junction material, here is one extreme of what happens in the baboon shunt, the evaluation of materials using indium-labeled platelets and fibrinogen and iodine-labeled fibrinogen. And on polydimethylsiloxane, circulation in the baboon produced a modest deposition on it, but not very profound. On a material which is 65% polyethylene oxide, of which the molecular weight is 20,000, very long chains, there's no deposition as seen by scanning electron microscopy, and there was very little deposition as noted by either radioactive indium or radioactive iodine, so neither platelets nor fibrinogen came down. But of course, as my distinguished colleague and ex-student Mike Sefton will point out, just because the platelets don't sit down on the surface doesn't mean that they haven't had a disastrous experience. So that's another story for another time. In any case, to make a comparison, one of the oddities of this was, if I had the same amount of, by volume, of polyethylene oxide, but the chains are only 2,000 molecular weight, not 20,000, it becomes a violently active material, far more active in bringing down platelets and ensuing fibrinogen and cells than either extreme, pure polydimethylsiloxane, silicone rubber, or pure polyethylene oxide. And as a brief mention, I would point out that over the years that I've worked, there are these 3 techniques: environmental scanning, electron microscopy, XPS, and Fourier transform infrared with multiple internal reflectance, which have come on since the beginning of Society for Biomaterials, which have enormously improved the understanding of surfaces. And back when we started, we didn't have these. And I might say also that back when I was an undergraduate at Harvard in chemistry, Frank Bovey and I were there at the same time, and it turns out we didn't even have infrared of any kind in chemistry. Now, in this last sequence, I bring you down on the right-hand side to ultra-high molecular weight acetabular prostheses. And one of my most recent and last students, Premnath Venugopalan, who graduated in 1997. And what he did, his thesis was on melt-irradiated polyethylene for use as acetabular cups. And this was in conjunction with Bill Harris at the Mass General Hospital, and it has been reasonably successful. For example, in one form is Duracell of Zimmer. Now, here is a little epilogue. These viscometers, I was involved with 3 viscometers, the Merrill Brookfield, the GDM, and some that I made which were disposable. This represents a total catastrophe and failure. There was never one Merrill Brookfield sold commercially, not one. Of the GDM viscometers, 5 were made for clients, and then nobody else was interested at $50,000 apiece. And as far as the disposable blood viscometers were concerned, I made, as Merrill Medical Company, about 1,000 of them, and lost, I would say, about $1,000, and gave the whole thing up. One of the reasons being, of course, that there's no way you can get paid for taking the viscosity of human blood, that no one will pay for it. Let me therefore conclude with my acknowledgments of greatest thanks to the Dewey and Almy folk, Bradley Dewey and Charles Almy, the President and Vice President, and Dunn Shanklin. Let me review my thanks to Roe Wells, Ed Salzman, my colleague for 25 years, Judah Folkman, where I was at Children's Hospital, Jerry Austin, who helped us from Mass General Hospital on the heart-lung machine, John Putnam Merrill, who advised us on the artificial kidney, Alan Callow, who supervised the work with me on Elliot Chaikoff, and last and certainly not least, William Harris at Mass General Hospital, with whom I collaborated on melt-irradiated polyethylene for the acetabular prosthesis. And then among my colleagues, I am particularly grateful to Gilliland and Draper, Gilliland of my department, Draper of Instrumentation Lab, because they were the ones that saved my bacon. Because back in these days, when I was up for promotion to tenure, the Dean, Gordon Brown, said, Merrill, you ought to get out of medical engineering and all this blood rheology stuff. You'll never get anywhere in chemical engineering with that. No one wants to hear about it. And Gilliland said to Brown, I think Merrill's onto something with blood rheology. That's why I'm here today, because of Ed Gilliland and the contribution of Draper. And now I come to another acknowledgement. This is a photograph by Kosh of Ottawa that got a little messed up. But I have to say, to this gentleman, I am enormously and eternally grateful, because he was the one that proposed me for all the awards he mentioned earlier. He was the proposer. Nobody else. He was the proposer. He got seconders, but greater love hath no man. Here is my optometrist test. This is the list of the presidents of the Society for Biomaterials, starting with Bill Hall and Sam Hurlbut and winding up with Nick Pepys today. And the reason for bringing it on the stage is simply to identify that I am responsible for 10.3% of those presidents as an instructor of them, namely to start with Al Hoffman, then Stu Cooper, and now Nick Pepys. So I take pride in having instructed them